Hi, my name is Jie Yu. I'm a PhD student at Norwegian University of Science and Technology. I will present our work about exploiting temporal information in echocardiography for improved image segmentation. Echocardiography is based on evaluating cineloops, where the temporal information is critical for diagnosis. This information is seldom fully utilized in image analysis based on deep learning because it demands a lot of time from clinical experts to do manual annotations. Besides, medical image datasets are often of limited size. From this video, we can see how few annotated images compared to the whole recording. Therefore, we found two opportunities to work with. First is that cineloops contain many images that are not utilized. Usually only 1 to 2 frames are annotated. Second is that temporal networks require annotations for the full cardiac cycle. However, having clinical experts to annotate the entire recording manually is certainly not the best approach. Based on the opportunities, we ask ourselves two questions. Can we exploit the temporal data using semi-supervision or pseudo-labeling? The goal is to obtain fake annotations as realistic as possible. Furthermore, can we use this to improve segmentation of the left atrium or left ventricle in echocardiography? First, I will go through the materials. We used 175 recordings from a Norwegian population study dataset HUND, including apical 4, 3, and 2 chamber views. This dataset was divided into training, validation, and testing set. We evaluated on 25 recordings including 7 frames each, 1 frame at the end of diastole, 2 systole frames, 1 frame at the end of systole, 2 diastole frames, and finally 1 frame at the end of diastole. Experienced clinical experts annotated the data. Here are some examples taken from the dataset. Due to previous studies, U-shaped convolutional neural network with skip connections outperforms in ultrasound segmentation tasks. On the same dataset, a more complex UNet achieved better evaluation matrix. However, our objective is to exploit the temporal information in ultrasound recordings, and we want to have a compromise between speed and accuracy. Therefore, we simply used a lightweight UNet which has only 1.9 million parameters, which can run in real time and has very similar performance as heavier ones. Long short-term memory (LSTM) was firstly proposed for natural language processing, which requires temporal memory to understand the whole context. Later, convolutional LSTM was proposed to capture better spatial-temporal correlations. Besides, to combine UNet and conv-LSTM, there are different possibilities to place conv-LSTM layers. Due to our experiments, the best space is to put them in each layer of encoder in UNet. Our objective is to exploit temporal data, achieving more annotated data without human involved. Therefore, we decided to adopt a semi-supervised method, which is called pseudo-labeling. We first train our baseline network using manual annotations at end of systole and the end of diastole, then use it to produce predictions of the whole cardiac cycle. After, apply automatic post-processing, which removes some errors. I will present the details later. Then use these predictions as new ground truths to train a new model. To remove abnormal frames, we first calculated dice between neighboring frames, then placed the ones that have a low score with interpolation. Also, we kept only the largest area for each class. Small areas and errors were deleted. Here are some examples where post-processing fixed some obvious errors. To have an overview of how different data materials and network structures perform, we compared 4 models. The first model is a baseline model that we trained only with frames annotated at the end of diastole and the end of systole, because these are the most used frames in the clinic, which are most probably get annotated. while Model 2 uses the same network structure as Model 1, but trained with pseudo-labels that generated based on Model 1. For Model 3, we hypothesize that Model 2's performance can be close to or even better than adding extra manual annotations. If so, we can see that pseudo-labels can reduce manual work and produce the same or even better result. Therefore, we train Model 3 to see how it performs when adding extra manual annotations. To achieve better temporal consistency, we added conv-LSTM layers to exploit spatiotemporal information. Here, we used the same pseudo-labels as Model 2 and a different network in which we have two conv-LSTM layers in each level of UNet's encoder. Here comes to results part. We first achieved some promising results with pseudo-labels on left atrium focused view images. Pseudo-labels and conv-LSTM solutions improved a lot the performance compared to the simple trained network. Then we further extended to more classes in left ventricle views. Firstly, we can compare Model 1 and 2. We can easily figure out that the pseudo-labels fix most of the obvious failures from the baseline model. Some people may argue that post-processing maybe can fix the errors as well. True, however, our lightweight neural network is much faster than post-processing, which allows real-time use in clinics. Although for evaluation matrix, Model 2 and 4 have very similar results. We can see from the video that Model 4, the one with the temporal block, is even more temporal consistent compared to the Model 2. If we look at the dice score and host of distance and videos, our pseudo-label solutions are quite close to Model 3, where we added more manual annotations. Here is a closer look at the two pseudo-label models. The two models have very similar values on dice and host of distance for tested frames. The model with conv-LSTM has better temporal consistency when training with the same data. Here is the left ventricle area trace. We can see from the figure that if only trained with maximum and minimum volume, which is the end diastole and end systole frames, the predictions area trace is the blue one. Segmentation might fail when the valve disappears, or the view looks a bit away from the standard. Pseudo-labels can fix this issue and achieve a very similar performance as adding more manual annotations at different time points. When comparing the performance of different models, I found a special case. The prediction of the left ventricle's area drops to 0 in the red trace, which is predicted by Model 4, UNet plus conv-LSTM. So what happened here? Here is the corresponding recording. Let's look at this sequence. During this period, we can see that the heart disappears from the image, while other models still try to guess something randomly. Model 4 decided to say that the structure didn't show up. This case will not happen frequently in reality, but does it mean that Model 4 understands better the context? Model 2 and Model 4 were trained using the same pseudo-labels. The difference is that Model 4 has conv-LSTM temporal layers, and the results show that it understands context better. However, we have another concern. Model 4, UNet with conv-LSTM, has more parameters because of the temporal layers. It has 5.1 million parameters. Does the number of parameters make it perform better? The answer is no. With an increased capacity of Model 1, baseline UNet still cannot recognize when the structure disappears as shown in image E. So conv-LSTM do have better spatial temporal understanding. Above was an interesting observation that we had. Besides, There are still some problems that we want to discuss and solve. For example, what kind of post-processing is most suitable? Our solution helps to improve performance, but still might fail if the first network's predictions fail continuously. In that case, interpolation will generate results from wrong frames. Another problem is how to balance between consistency and accuracy. There will be slightly compromise on accuracy to have better consistency. Maybe we need to decide on use case. In conclusion, posture labeling is a practical approach in medical imaging segmentation tasks to improve segmentation results, especially for those that lack manual annotations. On the other hand, posture labeling also provides the possibility to train supervised temporal models when the fully labeled dataset doesn't exist. For future work, we wonder if repeating the posture label process several times can improve furthermore the results. We think that the limit might be reached after a few iterations, but it is still interesting to see how much it can improve. Thank you for listening. Here's the discussion and question part.